Okay, let's pick up where we left off with this one. Again, go back, watch the bearings video first. Then this video talks about a plane heading from Chicago to Salt Lake City, Utah, heading on a bearing of 270 degrees. Okay, so the bearing is 270. That's measured from here all the way around to this direction. There's also a wind of 30 miles per hour coming out of the northeast at 225 degrees. That's this little piece right here, which might be hard to see from where you're at. It's hard to see because we use the length of the vector to describe its speed. Okay, 360 miles per hour would be this blue vector, rather long. 30 miles per hour, compared to that, very small. That's why the length of that vector is smaller. Now, the resultant speed and direction of the plane occurs by taking this vector here and adding it to the end of this vector, showing you the green vector. That's the resultant velocity vector for this plane. Okay? Now, in order to do this numerically or mathematically, we're going to do this problem similar to a resultant force problem that we did here. Okay? Where what we did here is we wrote the magnitude and direction angle for each of the force vectors, and then we converted them each into their real number format by just calculating this. And then we took those and added those components together, and then did our math with that to get the direction angle and the magnitude at the end. It's going to be the exact same format to this problem, but there's one extra layer to this. And that is to write the vector components for this airplane and for this wind vector. We have to write them in standard form, not in bearing form for those angles. Okay, so when I do this, I'm going to write this as, let's see, the velocity vector of the plane. So I'm going to say v sub p. That represents the velocity vector for the plane. Now, if you go back, and we've talked about this before, the speed is the magnitude. Okay, so that goes on the outside. Now, on the inside, we're going to write the cosine and the sine of the direction angle. But this is what I'm talking about. This is the extra layer. I'm not going to use 270 because that's an angle measured in bearing form from due north at 0 degrees to 270. Instead, I'm going to give the same representation of this angle measured from standard position. Now this one's pretty easy, I would hope, because it's directly east. We call that, or west, excuse me. We call that due west. Okay? Which, if you're measuring that angle from here, what's the measurement of that angle? That's 180 degrees. Okay? So we're putting 180 in here. We're not using the angle that's measured for the bearing. We're using the angle as it's measured from standard position. So we can, at this point, we're going to ignore these green numbers. Those were the bearing measurements. Okay? For the wind, we'll say VW, right? The velocity of the wind. Its magnitude is 30 miles per hour. Now, its direction angle, same thing. Now, for the sake of, actually being able to see this, I'm going to extend it. Okay, I'm not making it longer because it's increasing in magnitude. I'm just making it longer so we can actually see that angle a little bit better. Okay, the direction angle of this vector comes here all the way around, right? Now we said the bearing measurement was 225, and if you go back and you watch the first part of the video, that means that it was 45 degrees beyond this line. Okay, so the 225 degrees would go from due north here, 180, and then another 45 degrees to be 225. So if this is 45 degrees, if we just look at quadrant 3, and if this is 45 degrees, that means this piece is also 45 degrees. So, kind of a coincidence, should we say. The measurement of this angle, if I go from here to here, that's 90. to here, that's 180, and then I go another 45 degrees. What is that? 180 plus 45, it's actually 225. Purely coincidental for this problem, okay? The fact that 225 measured in this direction and 225 measured in this direction are in the same space, okay? Hopefully you're getting a handle on what it means to measure the angle in standard position, even though we're given a bearing. But those are the components for the velocity of the plane, the velocity of the wind. The resultant speed and direction, right? Speed is magnitude, and the direction, we need those components. So we're going to add these together. But just like we did in the force problem, okay, the first thing we're going to do is we're going to take the velocity of the plane and we're going to convert that into its real number components. So I'm going to calculate this and this, and I'm going to multiply that by 360. Okay, now, those of you that are super zen with the unit circle might not need to do that, okay, but since we have Desmos open, we're going to do it. 360 times the cosine of 180. Make sure you're in degree mode, okay? Make sure you click on the wrench, put Desmos in degree mode, because we're using degrees for these angles, okay? So we get 360 times the cosine of 180, and we get 360 times the sine of 180. So the components here are negative 360 and 0, right? So here, negative 360 and 0 take the place of these components. If you're like, 0, how do we get 0? What's the vertical component of this vector? How much is it rising up? It's not, it's going straight to the left. Okay, so it has no rise, it has no vertical component. That's why that ended up being a 0. Okay, the velocity of the wind, its components, 30 times the cosine of 220 and 30 times the sine, or 225, sorry. So we have 30 times the cosine of 225 and 30 times the sine of 225. Both negative 21.21. So we have negative 21.21, negative 21.21 for those components. Again, maybe this makes sense if you remember the unit circle stuff, but 225 degrees has the same x and y coordinate down here, right? They're both negative radical 2 over 2, negative radical 2 over 2 times 30. That's why we get the same number here. Okay, now for the resultant velocity, we had that as the green vector, okay? So the resultant velocity vector, if I add these together, I get negative 381.21, and I get negative 21.21, right? We're adding these to find the result of the plane with the wind. So we're adding these straight down, we're adding 0 to this, we get that same number. Okay, now take a look, just for the sake of comparison, just for the sake of, verifying whether we're on the right track. We said that by adding, remember this guy was real short. We said that by adding this to the end, because they were both traveling in the general direction of west or to the left, that was going to push the plane even further to the left, okay, and down a little bit. Look at the components of this resultant vector. The magnitude is a little bit longer than that, which is shown here in the picture. This length is a little bit longer than the blue length, and it's a little bit heading south now. That's the negative 21.21 that you see there. So these are the components of the resultant velocity, okay? But neither one of those tells me the speed or the direction. I have formulas for that, right? So, speed is magnitude. So now I want to find the magnitude of the resultant velocity. I'm going to plug these components into the formula that we have for that. Okay, to get my overall velocity. And then I'm going to, at the same time, set up the direction angle. Theta is equal to the inverse tangent of negative 21.21 over negative 381.21. Okay, let's see what we get for these. in Desmos. So we have the square root of negative 381.21 quantity squared plus negative 21.21 quantity squared. We get 381, let's call that 381.8. So this is 381.8. This is my magnitude measurement, and magnitude for what, the 15th time so far we've talked about? The magnitude of this velocity vector is speed. So it's 381.8 miles per hour, right? Now, as far as the direction angle is concerned, the inverse tangent function, the inverse tangent of negative 21.21, let's do this. We have negative 21.21 over negative 381.21. We get 3.18. Okay, 3.18 for this. Now, so approximately 3.18, degrees. What is that 3.18? We've seen a few of these problems now. 3.18 is talking about, you can hardly even see it, it's so small, right? It's talking about the reference angle. The angle formed by the vector and the closest x-axis. So that little guy is 3.18 degrees. Now, before we go into figuring that out, let's remember something, and I realize that this adds a lot of complexity for some of you, so just try to lock in. If you have to watch the video once or twice or slow it down, that's fine, okay? We're talking about the direction of a plane, which is measured with bearings. The direction of the plane and the wind were both given in bearing format, okay? So I'm gonna express my answer in bearing format, all right? So for the bearings, this was 0, this was 90, this was 180, and this over here was 270, you'll recall. Now, I'm writing those a little bit closer so that you can see. So the bearing of this airplane, when I express the direction, starts here and gets measured like this. Now, this airplane at this angle, the direction that it's headed in, this angle right here is 3 degrees. So if you start here and you come all the way around like that, you're stopping 3.18 degrees shy of that line for 270. So the actual direction of the plane is 270 minus 3.18, which is 266.82. This is the bearing, okay? This is not the angle in standard position. So we have two different measuring systems for the angles there, right? It's tricky, I get it.